Hello, Adimulam. Good evening. I'll start the session when everyone joins.
Okay, sir.
Do you have any questions, by the way?
Yes, sir.
So, yeah, if you have any questions, then you can ask till the people joins.
Sir, in early deadline first concept, sir has given a problem as assignment, sir.
Which one? Which deadline?
Earliest deadline first.
Mm-hmm.
Please explain me that homework problem, sir.
Yeah, acha, acha, in homework problem, right? So, wait, can you tell me the video number? Yes, Bhavya, can you tell me the lecture number? Bhavya, can you tell me the number of, video number or something?
No, sir.
Okay.
Sir, can I tell the problem, sir?
Yeah.
Okay. Sir has given that for task 1, the time period is 5 seconds and worst case execution time is 2 seconds.
Hmm.
And for task 2, the time period is 7 seconds and worst case execution time is 4 seconds.
Hmm.
The question is compare performance of RMS and EDF on this task.
The rate monotonic and EDF, right?
Yes, sir.
Yeah. So what problem you are facing?
Sir?
What problem you are facing?
Um, I can't understand the concept of EDF, sir, so I can't do that, sir.
Okay, I'll
Not
tell
able
you.
to do that.
See, first, earliest deadline first means whichever is having the highest deadline first, means that whichever is, whichever is trying to finish first. For example, let's say the period is 5 and the worst execution time is 2 seconds, right?
Yes, sir.
Acha, so first of all, you find out CI by PI. Okay.
Okay, sir.
CI by PI will be for task 1 2 by 5.
Sir, are you presenting your screen, sir?
No, I'm not presenting my screen. Should I present? It's just for you.
No, sir.
Yeah. No, I'm just asking, for example, let's say, first of all, you have to calculate the CI and PI of every task, okay? CI is the execution time, PI is the period. So if CI is the execution time, then let's say the value is 2 and 5. So what will be the execution time by period? It is 2 by 5, right? 0.4. Okay. And what about the other one? How much was it? 4 and 7, is it?
4 by 7.
Okay.
Yes, sir.
So it is, if it is 4 by 7, so it is, I guess, 0.54, something like that, right?
5, sir.
Yeah. So when you add them up, is it less than equals to 1?
No, sir.
Just try 2 by 5.
2 by 2 is less than 9. 1 by
Yeah. It is less than
it's
equals to
around
1.
0.97.
Yeah. So definitely it is possible through EDF. Yeah, earliest deadline first. So you have to check like that. Now, what about your rate monotonic scheduling? In rate monotonic scheduling, it is n into 2 to the power 1 by n minus 1. Okay, so n is 2. So there are two number of tasks. So the total CI by PI, the total value of CI by PI should be less than equals to n into 2 to the power 1 by n minus 1. So right now, can you calculate n into 2 to the power 1 by n minus 1? The value of n is 2.
4, sir.
Sorry?
4, sir.
No, not 4. N into 2 to the power 1 by n minus 1.
N is 2, sir, here.
N is 2. N is 2.
15, sir.
Hmm?
N is 2 to power n. So 8. 7, sir.
Yeah, it's again, so your total value 0.97 is less than that. So it is possible through both earliest deadline first and rate monotonic scheduling, right?
Okay, sir.
Got it? So, I mean,
Yes, sir.
that is the way you have to approach the problem.
Okay, sir.
Any other question?
Sir, explain the rules of priority inheritance protocol, sir.
Explain the.
Priority properties of priority inheritance protocol.
Can you speak clearly? I am not able to understand.
Properties of priority inheritance protocol.
Priority inheritance protocol. See, in priority inheritance, what happens is whenever multiple tasks are coming, okay, let's say what happens is you have many tasks with different priority. So let's say a higher priority task, okay, is taking control and uh, working on a let's say one resource, okay.
Okay,
Suddenly
sir.
it gets blocked. Why? Because it is blocked by the mutex which is taken, which is carried by the lower priority task. So right now what is the situation is the lower priority task is actually blocking the higher priority task. So at that time what happens is the lower priority task uh, inherits the priority of the block task. Okay, so though the lower priority task is having a lower priority, but still it can inherit for some time the higher priority task, and then what will happen is it will complete the task, it will leave, it will relinquish the control of the resource, and then finally the higher priority task will be able to move forward. So this is called priority inheritance protocol.
Okay, sir. Thank you, sir.
Okay. Any other questions?
Sir,
Yeah.
sir, why deadlock is not completely evolved, sir?
Sorry, why?
Deadlock is not completely evolved.
I'm not able to understand.
Sir, since deadlock is a side effect of priority inheritance protocol, why it cannot be completely evolved?
Why it cannot be completely avoided?
Evolve, sir.
Avoided, right?
I mean, no, sir, evolve. I mean,
Acha,
why it
okay.
cannot
Acha,
be?
can you do one thing? Can you write down the question? No problem.
Yeah, okay, sir.
Hmm. Why deadlock can't be evolved? Okay, just let me see. Who has posed this question? I mean, the question is not very clear. Why deadlock can't be evolved? Or is it resolved? Can you recheck the question once, Bhavya?
Okay, sir.
From where did you get this question?
I only got that, sir.
Okay, so can you, okay, if you have got it, then can you tell me what actually mean by that?
Sir, why actually it occurs, sir?
Why deadlock actually appears, right?
Yeah.
Yeah, see, deadlock happens when one task is waiting for the other task to give a resource to, let's say task A and task B both requires resource A and resource B, okay? Now,
Okay.
task B has taken control over resource A. Now, and task A has taken control over resource B, okay? Now, what will happen is, for example, let's say task B want to take control over resource B, then what will happen is it has, task A has to relinquish the control. Now task A can only relinquish the control when the resource B is available. Okay, so this way you see both the tasks are not able to move forward and they are in a deadlock situation, means they are in a stagnant situation. Was the answer clear, or do you now want some other example?
Sir, if deadlock cannot be resolved, sir.
Deadlock cannot be resolved. Yeah, deadlock can be resolved, but as such, there are many ways of resolving deadlocks, like aging and all. So, what will happen is the priority decreases as the time goes on. Okay, so that way you see that you know the deadlock can be resolved, but yes, if deadlock is there, then you have to resort to some other means to remove the deadlock. Okay, that is important.
Okay, sir.
Yeah.
Sir, explain about Khan process network, sir.
Sorry, which process network?
Khan process.
Can you write it down?
Yeah, sure, sir.
Yeah, so see, Khan process is a distributed model of computation, okay, in which a group of deterministic sequential processes communicate through, let's say, FIFO channels, okay. So what happens is you have three, let's say you have three tasks, okay, which is, but they are all deterministic. I mean, they, okay, so, I'll explain, pop in, yeah. So you see that they all are deterministic, okay. That what it means is that you know exactly when the task is going to start and task is going to end, okay. Then what will happen is when you have these three tasks running parallelly and they all interchange data through the with the help of FIFO channels, okay. Now this FIFO channels, if you see, the writing should be non-blocking, but the reading should be blocking, so that way you can synchronize between the process. Let's say the task A want to write some data to task B, okay. So task A writes the data, and then task A gets into some other activity. Okay, now task B, let's say, was waiting for the data. So unless and until the task B is, because the task B cannot run until and unless all the data is given to task B. So in that case, what will happen is task B will have a blocking call and task A will have a non-blocking write. Okay, so this is the whole the thing of the CAN network, that you have multiple processes and all the processes are communicating with each other. Okay. Bhavya, is it okay?
Okay. Yeah, okay, sir. Thank you.
So you should also know that CAN process, they were originally implemented, developed for modeling parallel programs. Okay. But right now, with the help of CAN process only, all this RTOS and everything is getting executed.
Okay, sir.
This multitasking and all, so everything. So question 9, week 9 assignment, question 9. Let me check. Yes, I think the answer that is given is wrong. Okay, in question 9, the answer should be D. Output does not depend on the input. Popin.
Sir, what do you mean by hierarchy communication FSM, sir?
Hierarchy communication FSM.
Yes, sir.
Well, wait. So it is like acha. So it is hierarchical state machine. So basically, let's say that you have S0, S1, S2, S3, S4. These are all states, right, in a state machine. But S0 is composed of other states, S01, S02, S03, S04. So that's why within one state you have multiple states. Okay, so that is called as hierarchical FSMs or communicating FSMs.
So that means instead of one state, there are multiple states.
Sorry.
That means instead of one state, there are multiple states are
No,
connected
no,
to
no,
S1.
no, no, no. It does not mean that. What it means is inside one state there is multiple states. In state machine, definitely there are multiple states, but inside one state, there are multiple states.
Okay, sir.
Okay, priority ceiling protocol with an example. Now we have spoken about priority inheritance, right? Priority ceiling goes more than priority inheritance. Okay, what it means is that in priority ceiling, let's say you take the same example where you have task A and task B. Okay, and task A, let's say, is a low priority task which was running, and suddenly task B has come. Now task B is a high priority task and task B is planning to run. Okay, but task A has got one resource of task B. Okay, so task B cannot run, but task B has to run because it has higher priority. So normally in priority inheritance, what happens is task A inherits the priority of task B, but in priority ceiling, what happens is task A is given the highest priority that is possible. Okay, so with that highest priority, you have absolutely no uh, blockage from any other tasks. You complete the task and reduce your priority and give the control back to the high priority task. Okay, so that is called priority ceiling. So in priority ceiling, a task is given the highest priority that is possible.
Okay, sir.
Just let me know if you have any questions. I'll drink water and come. Yes, Bhavya, how resource sharing will occur. See, what happens is resource sharing normally occurs with the help of either mutex or semaphore, but most importantly, it happens with the help of mutex. So what happens? Mutex is mutually exclusive, a mutual exclusion. Okay. So what happens? Mutex, you can say mutex is kind of variable. Okay. So whenever one task wants to use a resource, he achieves or he acquires the mutex of that resource. Now once the task acquires the mutex of the resource, there is no way the other task can use it. And let's say that after the resource utilization is over by task A, it will release the mutex, and then other task B can take the mutex. So this way, with the help of mutex you can use the same resource for by you can distribute the resource for multiple tasks. I am there in the meeting, so any questions anyone has, just either speak or put in the messages. Okay, round robin scheduling is used in those cases where all the tasks are having equal priority. By SDF, do you mean that static model? Can you put the full form of SDF?
Synchronous data flow, sir.
Okay, synchronous data flow. Acha, synchronous data flow is okay, I think, but on what context? Wait. Okay, so it is a whatever you are asking, is it related to Khan process? Khan process network. Okay, so in synchronous data flow, what happens is, see, the tasks are writing, right? Some writing them tokens and giving some tokens to other tasks and all. So this is known ahead of time. Okay, so this is predetermined. You cannot change it during the flight. So that is called synchronous data flow. So we know exactly, let's say you have 5 processes, we know exactly when each of the process will schedule the data, when each of the process will start that will start sending the data. So everything is very, very deterministic. So it makes the system very reliable. Yeah, okay, program state machine. Just hold on 2 minutes. Yeah, can you tell me that where have you got this program state machines? Because I can explain to you state machines, but program state machines is something that I am hearing for the first time. So can you tell me the video so that let me read and then I can tell you.
Sir, it is from lecture 36 video, sir.
Lecture 36, huh?
Yes, sir.
Yeah, thank you.
Could be included, and I show this is obviously is a completion that showing code. Okay, so S is assigned A plus 1, S is a signal, behavior B and another behavior C. How can we generate?
Hello, sir.
Yes, yes.
I have some internet issues, sir.
No problem, no
That's
problem.
why.
Yeah, Aditya Raj,
In lecture number 36,
yes, yes, yes. So I mean, I am not aware of this thing. So let me study it, and then maybe on Tuesday, can you remind me again?
okay, sir.
Yeah, just Tuesday you remind me. I'll explain to you in detail.
Okay, sir.
Thank you. Yes, Bhavya. State charts. Yes, we use state charts to have different states in system. So for example, let's take the example of a traffic light controller. Okay. So at one point of time, the output is red. At one point of time, the output is green. Another point of time, the output is yellow. So you see, depending on different conditions, you have different outputs, right? So that is best represented in a form of state chart. Of course, you can do it any other way, but that is best represented in terms of state charts. Yes, Bhavya, I'll answer this question. 2 minutes. Shankar, yes, Shankar, right. हाँ sure, बोला. अच्छा, अच्छा. Oh, nice. तो हाँ. Okay, okay. Thank you very much, Shankar. Thank you. Yes, Bhavya. Yeah. So, sorry, I was on a call. So, yes, in state charts, what happens is you have different events that are happening, right? So now what happens that whenever you have some event happening, that has to be communicated to all the tasks. So that's why, see, let's say that one event is specifically meant for task A, but how will the event manager know? The event manager doesn't know that. So the event is broadcasted to all the tasks or all the components. Okay, whichever components are excited by that event, they take it. So that is the reason we use broadcast mode of communication. So the events are broadcasted to all the components or all the tasks. Are you there, Bhavya?
Yes, sir.
Okay. Bhavya, will you be joining in the next Tuesday meeting?
Yes, sir.
Yes, sir.
Yeah, Aditya, please be there.
Okay,
I don't have a pen and paper this time, okay?
okay, sir.
Okay, sir.
Yeah, whatever questions you have asked, no? If you have not, you study that, and if you have not understood again, please ask me. I'll explain it
Okay,
again.
okay, sir. I will look into it and I will ask you on Tuesday, sir.
Right.
Okay, sir.
But whichever is clear by my explanation, it's fine. But whichever you are not clear, please ask me again on Tuesday, okay?
Okay, sir.
Okay with you,
Okay,
Bhavya?
sir.
Yeah, okay.
Okay, sir.
Any
Thank
other
you, sir.
thing? Yeah, any other thing? You can ask. I have still some time, around for 50 minutes. So yes, I'll be there if you have any questions, just post.
Sir, explain the timing constraints, sir.
Timing constraint means that whatever the task is supposed to complete within a time, na? So that is called timing constraint. Now in static, the timing constraints are more apt in digital system design. Okay, so what it means is, let's say you have two flip-flops and inside you have a combination logic. Now the combination logic will take its own time, let's say 5 nanosecond or 6 nanosecond to complete. So what it means is the clock to the flip-flop cannot be less than 6 nanosecond. Okay, so
Okay, sir.
that is called timing constraint of the whole design.
Okay, sir.
Okay.
Thank you, sir.
Thank you.
Okay, sir.